context-aware relative object queries to unify video instance and Panoptic segmentation. Recent transformer-based architectures perform remarkably well for image-level segmentations using object queries. However, their use for temporal tasks like video segmentation poses two main questions. How to produce temporally consistent object queries that model appearance and position changes of objects across frames. How to seamlessly propagate object queries while keeping the processing of frames online. To answer these questions, we develop context-aware relative object queries for video segmentation. Just one kind of object queries, continuously and seamlessly propagate across frames without any post-processing. Relative positional encodings capture position changes of objects in motion better than absolute positional encodings used in prior work. We match or surpass the state-of-the-art results on video instance segmentation, video multi-object tracking and segmentation, and video panoptic segmentation. Video segmentation is the task of segmenting and associating objects of interest in a video. Subtasks are defined in a community according to the objects of interest. For example, video instance segmentation involves segmenting diverse types of objects. Multi-object tracking and segmentation focuses mainly on cars and pedestrians. Video panoptic segmentation involves segmenting each pixel in a video frame. In this work, we are interested in known categories of objects, so we evaluate on these three tasks. As a natural extension to image segmentation, transformers have also been used in video segmentation recently. Some of these methods rely on local image-level object queries or global video-level object queries. For local object queries, video frames are processed independently. Image-level predictions can be merged using an additional association step, or predictions can be obtained using query vector propagation. For example, track-to-former propagates track queries and merges them with new object queries for each frame. Some methods also use global object queries where the entire video is processed at once. These methods fail to scale to long videos without heuristic clip merging. Intuitively, global object queries should be more accurate than local ones since they operate with a much larger temporal context. Surprisingly, this is not the case. The best methods on VIS like MinVis produce query vectors frame by frame independently. This raises the question, why do global object queries fail to accurately represent objects spatiotemporally? We study this carefully and observe that the object queries are often too reliant on the static spatial positions of objects in a few frames. They hence fail to encode the position changes well. This has not been observed before in the context of video segmentation. It also remains unclear how the queries can be seamlessly extended temporally while keeping the processing of frames sequential. To answer these questions, we develop context-aware relative object queries. These are continuously refined and propagated frame by frame. Spatiotemporal context is introduced to increase the temporal field of view. Use of relative positional encodings better capture position changes of objects. We use a meta-architecture like mask-to-former. Let tau naught be the first video frame. The learned embeddings QE are modified in the transformer decoder in the presence of multi-level image features U tau naught obtained from the pixel decoder. These act as context. Q tau naught represent meaningful object query, which produces the segmentation masks. We use relative positional encodings, which we shall discuss later. We first discuss the propagation. The object queries in the proposed approach represent all objects of interest in a video without the need to introduce new object queries every frame. Queries are activated if the objects they represent appear in a frame. In each frame, the objects are either expressed or nascent. The meaningful queries obtained in the first frame are propagated to the next frame. This happens iteratively. For video frame tau t, object queries q tau t-1 from the previous frames are propagated to the current frame and modulated. Since video frames change gradually, q tau t-1 already contains meaningful information for frame tau t. And hence, L number of transformer decoder layers are not necessary to modulate the object queries for the current frame. We skip the first few layers. Multi-level image features from multiple previous frames act as spatiotemporal context for frame tau t to increase the temporal field of view. A continuous refinement of the object queries permits to adjust to gradual appearance changes. Their propagation across frames helps to carry long-term temporal information so that they can seamlessly handle long-term occlusion, absence from the scene, or viewpoint changes. We now discuss the relative encodings. Prior work uses absolute encodings in the transformer decoder. The first layer receives a set of learned embeddings QE and the image features of a video frame, let's say U tau naught, summed with their respective absolute positional encodings. Each layer has a cross-attention operation that contains an absolute cross-attention matrix. This matrix is a dot product of linearly modified image features with its positional encodings and the linearly modified learned embeddings with the positional encodings. When the terms are expanded, we see that the last three terms incorporate positions highlighted in blue. We experimentally find that the last three terms introduce undesired dependence of object queries on spatial positions in images. As a modification, we introduce relative positional encodings. The cross-attention now has a relative cross-attention matrix defined as shown. The relative positions xi-rel are learned as proposed by Dai et al. For language modeling. We evaluate on the three tasks mentioned before. On video instance segmentation, our approach surpasses MinVis on the complex OVIS dataset. In multi-object tracking and segmentation, we obtain the best results even when compared to highly specialized methods like point track. On video Panoptic segmentation, we perform similar or better than highly specialized two-branch architectures like VIP DeepLab and VPSNet. We now see that performance drastically improves when using relative positional encodings instead of absolute ones. This can be seen in the association accuracy or ASA, detection accuracy or data, and hence the overall accuracy HOTA. In this example, we observe multiple identity switches for mass-to-former VIS. We verified that this is due to the absolute positional encodings. The identity switches are resolved when using relative encodings as seen in the bottom row. Our method retains identities of objects under drastic viewpoint changes, long-term occlusion, and for challenging scenes. Visualizing entire videos show the consistency of object identities. To summarize, in this work, we introduce context-aware relative object queries, which are continuously refined every frame and propagated across video frames seamlessly. The relative positional encodings better capture position changes of objects. Our approach is general and effective. It reaches or surpasses the current state of the art on three challenging video segmentation tasks. Thank you very much. Please visit our poster on Tuesday afternoon and read the paper for more details.